Hello and welcome to a digital lecture for Calculus 2 at Salt Lake Community College, and what will be the last video for Calculus 2 at Salt Lake Community College. In this video we're going to be talking about the equations of lines and planes in three-dimensional space. Now, to talk about that, I think it's best to consider what you need to make a line. And all you need to make a line is a single point and a direction. As long as you know a point and a direction to follow, then you can create an entire line. In this case, what we're going to be using is a point and also what we call a direction vector. That direction vector just being just some vector v with components a, b, and c. If we have that, then we should be able to define a line defined by all points in the set P, such that from your initial point P0 up to P, any point on that line, that should be a parametric version of that direction vector. Parametric because it depends on how long you need to go in order to get to any single point. If you draw a vector starting from the point, draw a vector to the starting point P0, so if you're on a three-dimensional plane and P0 is over here, if you draw a vector that goes up to that point, if we call that R0, and then if this is supposed to sit on a line like so, then you can also consider any other vector that goes up to that line. Maybe this one right here, we'll call that R. Then what we're really looking for is a vector that defines this right here, that defines the equation of the line. And that right there is the difference between the two vectors R and R0. So this is the difference of the two, R minus R sub 0. That's what this defines. And then if we parametrize that, we'd be able to get the entire line, because that would just be extending it or minimizing it. And so if we set instead P sub 0 to P equal to R minus R sub 0, the vector that defines that, you can also set that back equal to TV. And then solving for R, which is what we need to know these different equations, these different vectors that go up to this line. If we could define all those values R, then what we get is the vector equation of the line as R equals R sub 0, which is the point vector, the one that goes up to your initial point, plus TV. Where again, T is a parametrized equation, and V is the vector itself. So that's one way of finding the vector equation of the line. From this, we get something that we use much more often, which is called the parametric equations of the line, where you're just looking at each individual component. If this is true for the entire vector, then you should be able to split that up into the components for x, y, and z as the initial point x sub 0 plus at, the initial point y sub 0 plus bt, the initial point z sub 0 plus ct, where a, b, and c are points or are the components of the direction vector. Furthermore, if you take these equations and solve them for t, so for example this first one, if you subtract x sub 0 over and divide by a, you get x minus x sub 0 divided by a equals t. You should also be able to do the same thing for all these other equations. For example, if I do that for y, I get y minus y sub 0 over b, and that also equals t. And so, these equal each other. And you could do the exact same thing for z to get z minus z sub 0 over c, and what these are called are the symmetric equations of the line. These are kind of nice and clean, small equations that you can use, and yes, there will be two equal signs there, to demonstrate what a line can look like. Because really, if you set any two of these, if you say take these first two, what this actually defines is an entire plane. And then when you take another pair, maybe these two, this defines another plane. And any cross-section of two planes will just define a line itself. You could think about a plane like this, and then you could think about another plane that goes through that, like this, and they intersect along this line here. So that's another way of defining a line itself, by thinking about the cross-section between two planes. Now with those in mind, we're going to do a couple examples. First, we're going to find the parametric equations for the line that goes through these 2 points. Now, from what we need for the parametric equations of the line, we need both a point, which we have 2, and we need a direction vector. So we need a vector that defines what direction this line will go in, and since we have 2 points, we should be able to find that simply by subtracting the coordinates there. We should be able to create a direction vector by saying v is equal to the subtraction of these 2 points. You can do it in either way. I'll say the second minus the first, so 5 minus -3, and then -6 minus 1, and 8 minus 5. This gives me the vector of 5 plus 3 is 8, -6 minus 1 is -7, and 8 minus 5 is 3. So this is a vector that goes from this point to the second point, so from point 1 to point 2. That's what this vector defines. And that would be the direction vector, right? Because I could put that vector anywhere. Maybe that vector doesn't necessarily sit on those 2 points right now, but this direction vector starts at the origin and goes up to this, so it's parallel to what we want to make. And therefore, we should be able to make the parametric equations using either of these. Maybe I'll use these ones. And I'll say, okay, x equals the first point, -3 plus 8t. Maybe I'll put these in red so you'll notice where these are coming from. So 8, -7, and 3. So this is 8t. And then y equals another point 1 minus 7t. And z equals 5 plus 3t. So this would define parametric equations that go through that line with that one initial point. However, I could have also used the other initial points. Maybe I used P2 instead. Well, then that would be x equals 5 plus 8t. Then y equals -6 minus 7t. And z equals 8 plus 3t. This would be another set of parametric equations. So I'll say this is set 1 and this is set 2. Another set of parametric equations that define the same exact line. They don't start at the same place, but that's fine. You can define a line starting at any given point. Therefore, what this also shows is that just finding a parametric equation of a line, those aren't necessarily going to be unique to that line. There's many other ways to represent that line using different parametric equations. Let's do a second example. Second example for symmetric equations, these are very easy. A symmetric equation of the line that is parallel to the vector v, or 4, 6, -1, and goes through -4, 5, and 10. Okay, well, for the symmetric equations, all we need, as shown above, is x minus x0, y minus y0, z minus z0. So this is going to be x, y, and z subtracted by the coordinates of an initial point. Each of those divided by a, b, and c, which are the components of the position vector, or the direction vector, rather. So that means we're just going to have x minus, or plus 4, I guess, divided by 4. And then for y, we have y minus 5, so it's a point, divided by the component 6, and z minus the point 10 divided by the component -1. And that's all we need for the symmetric equations. Any points x, y, and z that satisfy these symmetric equations would be on the line. Note that if it is the case that there's some component that is a 0, then all you would do is separate one of these out. For example, if this was 4, 6, 0 instead of -1, I would have the first two equations, and then for the last one, I'd consider the parametric equation for z as z equals z sub 0 plus ct. I'd set c to be 0, and I'd just have z equals its point 10. So I'd have the two symmetric equations and also z equals 10. That would also define any points that satisfy those as being on the line. Okay. I also put that note in the symmetric equations right here. So that's how you deal with lines, more or less. There's other ways, but those are the primary ones. Now, in order to talk about a plane is a little bit different. The best way to consider a plane is first to consider its normal vector. If you have a plane like this, the normal vector is the vector that is 90 degrees with that plane. And that normal vector can be created by the cross product of any two vectors that define that plane. So, what we're going to think about is that normal vector n, which we'll define as a, b, and c. I like to use capitals to really differentiate it. And all we need is that normal vector and any point on the line, or any point on the plane. So, x0, y0, z0. Any point. Any point in that normal vector can help us define the entire plane itself. Now, we know also, other than the cross product, we also know that the dot product of any two perpendicular vectors is 0. So, any other point on the plane with that initial point, that will define a vector such that the dot product with the normal vector should equal 0, because the dot product of two perpendicular vectors is 0. Therefore, if you consider from initial point to any other point on the plane x, y, and z, you can define that as a vector x minus x0, y minus y0, z minus z0. And then if you dot product that with the normal vector ABC, which would multiply the components together, you get what is called the standard form for the equation of the plane, as shown below. A times x minus x0, b times y minus y0, and c times z minus z0, where a, b, and c come from the normal vector, and x0, y0, z0 are some initial point on the plane. If you were to multiply this out, distribute, and then you get a, b, and c multiplied by those constants x0, y0, z0, you should be able to combine all these constants together into just a single constant d. Move it to the other side, and you get what is called the linear form for the equation of the plane, which is just a, b, c of x, y, and x, y, and this should be z, equals to d. Now, notice the linear form for the equation of the plane. One of the most useful things is that it retains a, b, and c, the components of the normal vector. So if you have an equation of the plane, you should be able to come away with the normal vector pretty easily. Now, what we're going to do in this third example is we're going to take three of these points, these three given points here, and what we're going to do is find the equation of the plane that goes through all three of these. Well, in order to find the equation of the plane, what we need is a normal vector. If we can have a normal vector, then we're okay. Well, we know that we can create a normal vector using the cross product of two vectors on the plane. So what we're going to do is take one of these points, we'll consider it the initial, we'll create two vectors from that, and then find the cross section to establish the normal vector. So if you think about maybe point, I'll say that's 1, 2, and 3. We're going to define two vectors, whatever two vectors you want, and then the cross product of that should define the normal vector. And then we have a normal vector and any point on the plane, and we should be able to come up with the equation of the plane itself. So I'm going to choose arbitrarily. I'll choose the second one. If you want to choose the first or third one and see if you get a similar thing, go ahead. I'm going to choose the second one as my initial point to create two vectors off of. So I'm going to say, all right, P2 to P1, that I'll call V, and that's going to be the difference of the values from P1 minus P2. So that's going to be 1 minus 4, and then negative 2 minus 1, and then 3 plus 2. So that's going to be -3, -3, and 5. And I also have P2 up to P3, which I'll call W for sake. And then I'll say -2 minus 4, -3 minus 1, and 0 plus 2. So that should give me -6, -4, and 2. So this is V and this is W. Those are two vectors on the plane, and therefore if I take the cross section of that, that should equal the normal vector n. And the cross section I'm going to do algebraically. If you want to take a minute and do it with matrix multiplication, if that's more your style, then go ahead. Make sure you get the same thing I do. So I'm going to do it algebraically because that's what I'm more familiar with. -3 times 2 is -6. And then -5 times -4 would be plus 20. 5 times -6 is -30. And then minus -3 times 2, which would be, that's -6, so plus 6. And then lastly, for the third component, we have -3 times -4 is 12. And then -3 times -6 is 18, and we subtract that. So we get the normal vector to be -6 plus 20 is positive 14. -30 plus 6, that one's negative. That's -24. And then 12 minus 18, that's -6. And that's our normal vector. So now we have all the components we need. We have the normal vector, we have a point, and we should be able to come up with the equation of the line using the equation right up there. So I'm going to take my component, maybe I'll do this in red again so you notice this. So 14, -24, and -6, so you know where these are coming from. I'm going to take 14, and I'm going to multiply that by x minus x0, which I'll just use the point that I started with, P2, 4. And then we also have minus 24 for y, and that's going to be y minus 1. Then minus 6 for z, that's going to be z, that's plus 2, equals 0. If you get a different equation or a different looking one, you should be able to maneuver things around and still get the same constant on the other side. This will give us 14x. Yeah, I'll just do this in black. 14x, this will give us minus 24y, and then minus 6z. And on the other side, we get 14 times 4. That is 60, no, that's 56. 56. So negative 56. We also get a positive 24, and then we also get a minus 12. If we add those together, you get 44. Negative 44. Then you add that to the other side, so you get positive 44 over here. Okay, so I just distributed out 14, -24, and -6, and then I added that negative 44 to the other side of the equation. So I don't have it equal to 0 anymore. And that should be the equation of the plane. A little bit of extra work we needed to do to find that normal vector, but not too bad. Lastly, what we're going to do is talk about the distance. We know how to do the distance from one point to another. We did that a while ago in 12.1. But how about a point to a plane? Well, if you let some initial point p sub 0, so if you're looking for the distance from a point p1, if you take some point p sub 0 that's on that plane, then you should be able to find the distance, or you should be able to make a vector that's the difference between those two as x1 minus x0, y1 minus y0, z1 minus z0. That should define some vector, but if p0 is any point on that plane, I don't necessarily know if that's going to be a straight line. I don't know if that's a perpendicular vector or not. I could have a plane like this, and I'm considering maybe p sub 0 or p sub 1 is over here, and p sub 0 is right there. And what I just built is this vector. that vector might not necessarily have a right angle to this plane. So what I actually need is I need to make the projection down to the plane that has a right angle. And specifically, I don't need the full projection vector. What I just need is the length of this right here. I just need the length of the projection itself. If I can find that, then I'm good. And to find the length of the projection, you just take that dot product of the two vectors and divide by the magnitude of the normal vector. So, for a plane that has A, B, and C, we know what the normal vector is. That should be pretty obvious to get. And so, the dot product for m dot n, where n is the normal vector A, B, C, you get ax1 minus x0, by1 minus y0, z0, z1 minus z0, over the magnitude, which is the square root of a squared, b squared, and c squared. And then if you were to take a and b and c and distribute that out, you get a times x0, b times y0, c times z0, which we talked about before. You can combine into a single constant, and we can call that constant d. So therefore, what we get is not the linear form for the equation of the line. What we get is the distance from a point to a plane as the absolute value of ax1, by1, c, z1 minus d, which is basically just plugging in the point into the equation of the plane itself, divided by the square root of the normal vector components, a squared, b squared, and c squared, but all of which can come from the plane itself. So then let's try that. Let's find the distance between two parallel planes. 3x minus 4y plus 5z equals 9, and 3x minus 4y plus 5z equals 4. So this may look kind of odd to consider, and I'm taking a little bit of an extra step, but all we really need to do, if we need to find the distance between two planes, I just need to find one point on one of those planes, and then find the distance to the other. That's all I need to do. So I can do that in a few different ways. I personally see that first equation, and I see that 3x and 9 match up pretty nicely. So if I set for plane 1, if I set y equals 0 and z equals 0 just to come up with a point on that plane, I should be able to solve and say 3x minus 4, 0 plus 5, 0 equals 9. Therefore, 3x equals 9 and x equals 3. So I now have a point on plane 1 as x of 3, y of 0, z of 0. So now I have a point to work with. Now that point is on the first plane, and I need to find the distance from that point to the other plane. So I need to find the distance from 3, 0, 0 to 3x minus 4y plus 5z equals 4. If these two planes are parallel, then the distance from any 2 points, or any 2 points that are perpendicular to both planes, would be the same. So what I get is L, the length, is going to be the absolute value of 3 times 3 minus 4 times 0 plus 5 times 0 minus 4. So we're supposed to subtract d, and d is on the other side, so we have to move it over. That would be me plugging in that point into the second equation. And then divided by the magnitude of the components, 3 squared plus 4 squared plus 5 squared. Technically it's negative 4 squared, but whatever. That gives us up here 9 minus 4 is 5. And on the bottom we have 9, 16, and 25. 9, 16 is 25. 25 and 25 is root 50. Root 50 is 5 root 2. And then that's 1 over root 2, or if you rationalize, root 2 over 2. So that's the distance between those two parallel planes. Side note, we know that they're parallel even just looking at the normal vector for both of them. 3, -4, and 5. That's the normal vector. Is 3, -4, and 5. Or vector, not point. So since they both share that same normal vector, they both are parallel to each other. But with that said, that's it really in terms of dealing with lines and planes in the three-dimensional scape. If you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. But with that said, I hope you have a nice day.